My name is John Glorieus. I'm working already more than 16 years for Yaskawa. Started as an application engineer, switched to key account manager for Benelux and France, then becoming group leader of the total solution teams. And the last 5 years, I was the product manager for the new iCube control platform. And together with the R&D team in Nuremberg and America, we've developed the first product in the iCube series, the iCube 9200. If you have questions during my presentation, you can always write this in the Q&A or in the chat. I have my colleague Sven Schöneberg here online, and he will try to answer your questions immediately. So, coming back to the title of this presentation, what are exactly the economic challenges that we all encounter? To find an answer to this question, I looked to the Insight report of the last World Economic Forum in Davos. And here you can find a list of global risks divided into different categories like social, geopolitical, environmental, and so on. But the category that we are looking for is the category economic, which is split into 7 challenges. The first challenge is inflation and economic downturn. This is a challenge where Yaskawa has no influence, but this will cause a survival of the fittest among companies. With our new automation platform, Yaskawa will bring you in pole position in this rat race. A second challenge is disruptions to important supply chains. Last week, it was already 5 years ago that we've started our global COVID-related lockdown and the biggest disruption of our normal life we've ever seen. Russia's invasion in Ukraine, pirates attacking general cargo vessels, and so on. These are some of the reasons that influence the global supply chain of goods. But Yaskawa learned his lesson, and we've made ourselves more resilient against future supply chain problems. Yaskawa invested in factories all over the world, also in Europe. And now we have 6 production sites in Scotland, in Sweden, 2 in Slovenia, 1 in France, and 1 in Germany. The third challenge is the asset bubble burst. Prices for housing, investment funds, shares, and other assets become increasingly disconnected from the real economy. And the fourth one, public and private debt, corporate, household, or public finances are struggling to service debt accumulation. This is resulting in mass insolvencies and sovereign debt crisis. Yaskawa has an answer to a lot of challenges, but for those 2 challenges, we don't have an answer. So I will not come back to those 2 challenges that came out of this web forum. But the 5th one, talent and labor shortages. Some years ago, we talked about the war for talent, but now it feels like the war is deepening and we can talk about war for labor. Means Yaskawa's solution for this challenge is obvious. We have automation and we have robotics, so we can solve this challenge. The 6th challenge is crime and illicit economic activities. So cyber attacks are on the rise, and ransomware and phishing scams are now a common occurrence. As businesses become more digital, they also become highly attractive to cyber criminals that intend to steal data and hold organizations hostage to monetary demands. Our new ecosystem has a dual track solution to beat these cyber criminals. And the 7th challenge is sustainability. The climate change is the world's largest business challenge, and consumers are demanding more eco-friendly products and services. But becoming more sustainable doesn't have to be only to satisfy the consumer's needs. It can also help you spot efficiencies and savings that you can have that can have a positive effect on your bottom line. Also here you will see in the next couple of slides how Yaskawa can support you. So during my presentation, I will refer to these challenges, except 3 and 4. In a world full of technology, AI and IIoT can help us finding answers to some of those challenges. But what does it mean, AI and IIoT? And how can this help us in the industry? And everybody knows IoT, but what is the difference between IIoT and IoT? So IoT is only aimed at the average consumer to make our life easier. IIoT is used in industrial plants and focuses on interconnectivity of hardware and software. But both IoT and IoT are neither devices or sensors. It's an ecosystem based on communication. It's a virtual platform where IT meets OT. And the target of IoT is to make our life easier. We save energy at home, or we have safety at home, or we check our health. And here is exactly the difference with IIoT, where the target is to improve business performance. But now you will ask me, how can IIoT improve the business performance? Well, this improvement is created through several capabilities, and I will explain this with 6 examples. So the first one is decreased downtime. With predictive maintenance, we can prevent breakdown on the machines. This will help you with challenge 1, inflation and economic downturn. It's obvious because the OEE will be much higher if the machine never stops. And with challenge number 5, talent on labor shortage. This needs maybe a small explanation. I believe we all know a maintenance manager, mostly an older people, who comes on the factory floor, and by the smell and the noise, he can tell you which machine needs maintenance. But exactly these valuable people will disappear soon, and they are irreplaceable. To avoid this gap, IIoT will help you with predictive maintenance based on data and theory, and no longer on sentiment. The second example is remote control. Adjusting or optimizing machines remotely saves the engineer a lot of time, where he can do other things. It saves your company a lot of money, and it saves the planet a lot of CO2 because we don't need to fly. So that's why we can say that this helps you with the challenges 1 and 7. Example 3, improved security. We are aware now that we need to protect us against unapproved admittance and data loss. So this helps you fighting against challenge number 6. The 4th example is smarter decision making. This is possible by collecting data from smart sensors, which gives you a deeper insight into production. With this deeper insight, you can optimize your production process, so challenge number 1, and your supply chain, so also challenge number 2. The 5th example is improved ROI. So if we can improve, for example, the energy consumption of your production line, we can minimize the production cost and we can improve the ROE. So this helps you encountering the challenge 1 and 7. And the last example is improved productivity. Collecting data about the equipment, the methods, and the properties the machines are using will lead to an improved productivity. For example, by removing the bottlenecks that you encountered. So this helps you also fighting against challenge 1 and 2. But now the question will pop up, why didn't we use that already 20 years ago? It's a good question, but also the answer is easy. We didn't have the equipment and the know-how for this. The key to successful IIoT is AI. And what does it mean, AI? And what about machine learning or deep learning? If we look to this process here, so we have fruit that needs to be sorted. If we really have a close look to this automation process, the success of this automated system is a scanning system that informs the algorithm based on labels, what kind of fruit it is. The algorithm has been hard-coded by humans. A PLC programmer made this, and this is one of the first examples that we have in the past with AI, but without machine learning and deep learning. So in a later step, we used machine learning. A machine learning based algorithm is to solve a problem of fruit sorting by enhancing the artificial intelligence based approach. When labels are not present, but the definition of what each fruit looks like is available, this is called feature extraction. And to do this, characteristics and attributes that identify each fruit are used to create a blueprint. Characteristics such as the size, the color, the shape. If it's long and it's yellow, it's a banana. Okay. These characteristics are extracted and used to train the algorithm to classify the fruit. The next step we had is deep learning. Here, the algorithm is now proposed to solve the problem of sorting products by totally removing the need for defining what each product looks like. By providing the deep learning model with a lot of images of the fruit, it will build up a pattern of what each fruit looks like. The images will be processed through different layers of the neural network within the deep learning model. Then each network layer will define specific features of the images, like the shape of the fruit, the size of the fruit, the color of the fruit, etc. A deep learning based model, however, requires a significant computing power and a huge amount of data. And that exactly is the problem we had in the past. We didn't have those two requirements available. But in the computer world, time flies, but not with the speed of a bird, but with the speed of light. This means that this deep learning is getting increasingly common today because 3 new features came up and we have an easy access to a huge set of labeled data. For example, ImageNet has thousands of labeled pictures of different objects and all for free. A second feature that came, the increased computer power, not only hardware with GPUs, but also in the cloud. And the third one is pre-trained models built by experts are online available. For example, AlexNet can be retrained to recognize other objects. This is one of the reasons why ChatGPT is getting more and more powerful. As you can imagine, the cloud is becoming more and more important, and that's the reason why big IT players are entering now also in the OT world. The 3 main cloud providers are AWS from Amazon, Microsoft Azure, and GCP from Google. They almost offer the same services, but Amazon is the best all-rounder. Azure, of course, is the best suited for Microsoft services, and Google is the best in big data. They have already some nice applications, but mostly for very large companies like NASA, Boeing, Ford, and Nike. To get in track with those new developments, Yaskawa started the development of a new machine controller, the iCube control. This iCube control, the brain of it is the Triton chip, developed by our own company, ProfiChip. This Triton chip has a 3-core ARM processor with a clock speed of 1.2 gigahertz, which we need for the high demands on synchronous movements that we have. compared to other processors, we also have a much lower power dissipation, and derating starts only at 60 degrees ambient temperature. Therefore, we do not need a fan, which is very important in certain industries. So this feature helps us with challenge number 7, the sustainability. The iCube has also an integrated safety master with FSOE as network safety profile, which can meet SIL 3 requirements. So you get more for a smaller price, helps you for challenge 1. The iCube has a modular design built on a real-time Linux system, which we developed together with Phoenix Contact. This helps you also tackling challenge 1, because we make sure that you only buy what you really need for your application. Our main network for motion is EtherCAT, but we also support other networks such as Profinet, OPC-UA, Modbus TCP, and Ethernet IP. So if your supplier can't deliver your product with a Profinet connection, for example, you can easily switch to the same product, but now with an Ethernet IP connection, for example. So your supply chain is flexible. Another great asset is the freedom of programming. So you can program not only in IEC 61131, but also in C#, C++, Python, Java, MATLAB Simulink. It's all possible. So you can really choose the language you know the best. So this will help you finding the right people for your R&D department. So I explained before that the cloud is getting more and more important. But how can we connect our iCube to the cloud? There are several ways, but we start with connecting the iCube over one of those 2 Ethernet ports to the Ethernet. Internally, these 2 ports are switched, but if you need 2 separate IP ranges, we can open the switch. Since our platform is based on Linux, we can run all different kinds of Linux apps on our platform, even in containers. In the App Store, you can choose which app you want to use. For example, the Xon Cloud app has a remote VPN access, or for data logging and alarming, or for MQTT data transfer. Another possibility is the ProfiCloud connector app for connectivity to the Phoenix Cloud. And another one is the IIoT library app for connectivity via MQTT to clouds like Azure, AWS, GCP. So this helps you encountering challenge number 7. Decreased downtime can be achieved by using predictive maintenance, which prevent breakdowns on the machine. The iCube will collect all necessary data from the server pack and send this to the machine learning algorithm, which is trained on the Yaskawa product. This algorithm will then predict when a slider needs to be lubricated or when you need to tighten your belt or whatever. So this helps you replacing your overaged maintenance manager, challenge number 5, but helps you also planning your maintenance in such a way that downtime of your machine is reduced to a minimum. But what you hear a lot in my presentation is sending data to the cloud. This means that your machine needs to be online. And then we should protect the system against unapproved admittance and data loss. So iCube developed a dual way of security with integrated security functions and settings in the WBM. The first one, the built-in features are based on the Linux operating system, and they have services like a firewall, OpenVPN, SFTP server, and so on. And the second one, the settings that you can do with the WBM manager, like security profile that you can set up. You can have a user authentication. You can have a syslog configuration. So this all are features that need to be updated constantly. And that's why we grounded a new department. We have now our own cybersecurity department. So this is obvious. This is how to tackle challenge number 6 with this feature. With our iCube, you have also the freedom of field bus choice. Like I said before, you can simply continue to use the devices that you control via EtherCAT, Profinet, Modbus, OPC, OEA, or Ethernet IP. The only restriction we have is EtherCAT is the only field bus for real-time motion commands with the FMK, with the flexible motion kernel. But we had our reason why we used EtherCAT, and that's why you find here some advantages of this EtherCAT as a motion bus. First of all, we can continue to operate your favorite product via EtherCAT. There's a uniform programming and configuration because we use standard EtherCAT objects. We don't have proprietary objects, it's really all standard EtherCAT. The Hot Connect feature allows you to build your machine in a modular way. And other slaves from third-party suppliers that support distributed clocks can be updated deterministically. So this is the way how we defeat challenge number 2. I will show you briefly how we can add a product from a third-party supplier via an ASI file to our platform. So first of all, we open a project. Then we go to the file and we go to import, and there we choose import ASI files. Then we search for the correct folder on our PC and select the correct XML file. Then you can check if you selected the correct product and click OK. Hopefully the snack bar will tell you that you imported this device successfully and that you will find it in the device catalog. The device catalog is on the right side, and if you click a few times, you will find exactly the device that you imported. Now you can manually integrate your device in the EtherCAT device list of the plant. So the left side is the plant side, and there you can choose the stepper module that we integrated. If you open now the property windows for your device, you will find all the parameters that the provider of this device makes available for us in order to operate this device in the right way via EtherCAT. So you see here error code, set point, control word, and so on. You all find this as parameters. So not only we have a freedom of field bus, but we also have a freedom of programming with iCube. But also here we have some restrictions. Not all languages can be used for all purposes. So that's why we should have a closer look to our iCube architecture. This is the architecture, and we can draw 2 lines over this architecture. The first line divides the platform into synchronous or asynchronous execution of your program, and the second line into running your program on the iCube platform or remote. In this way, we divide our architecture in 4 quarters. The first quarter is synchronous execution running on the iCube. The second quarter is asynchronous execution and also running on the iCube. The third quarter is asynchronous execution but remote, and the third quarter would be synchronous execution and remote, but this is not possible. So the first quarter means a program which runs in a real-time task on the iCube. This can only be programmed with IEC 61131, C++, C#, and MATLAB Simulink. The second quarter is running directly on the Linux platform, but the code will run asynchronously to the real-time task of the iCube. And the third quarter is to run the program on an external PC, but also asynchronously to the iCube real-time task. So first, let's have a look to the first quarter and the possibilities how to program synchronized to the real-time task. We can write functions, function blocks, and POUs in C++ and C# in Visual Studio or Eclipse. Currently, we do not support MATLAB Simulink at Yaskawa. Phoenix and the PLC Next, they have that already, but we didn't implement it yet. What are the advantages of C++ and C#, and why should you use it? Advantages are there are a lot of reference libraries available, for example. Another advantage is that for every 5th engineer who knows C#, there's only a half of an engineer who knows ISC 61131. Also, there's a lot of online help available. There's a good version controlling. Easy comparison is possible. And a good IP protection is possible because the source code is hidden in an ISC 61131 library. So for programming in C#, Yaskawa delivers a toolchain with functions, function blocks, and programs. And this, like I said, for Visual Studio and Eclipse. Now I will demonstrate how a C# program can be integrated in an iCube controller as a library. The public classes that you define here will pop up as a function block in the iCube engine. In this example, this string example FB, after compiling your project in C#, you have 3 different file types that are generated: a DLL file, a PCWLX file, and a PDB file. This PCWLX file, that's the file that you need to copy in the iCube Engineer library folder. If you do so, you can add this code as a user library in your project in iCube Engineer. You can now add the classes that you defined in the C# as a function block in your IC library. So here, all the functions that you see, that were the classes that you defined in C#. Okay. How can we integrate now C++ in our iCube environment? For that, we offer you, or we deliver you, a C++ SDK, software development kit, that we deliver also for Visual Studio and Eclipse. And we have here 3 different project types that you can use. First of all, the PLM, which can run as a POU in a cyclic deterministic task. An ACF, the application component, which can run on the Linux section of our controller, and their execution is triggered by remote service calls. And the last one is consumable library project, is just code that can be used in other projects. I will demonstrate how to integrate a C++ code as a POU. So we first configure the in and out variables of the program. Then you program your C++ code in the C++ environment. But after saving and placing the file in the right folder, it will pop up in the component tree in the PLC Next component folder. You need to configure this POU in the ESM task, where it will run as a real-time synchronous POU within an IEC task, for example, in the fast task. Communication with the other POUs is done with in and out ports on the global data space. So in the watch window, we can now force the variables, and you can see immediately what the program is doing with the output. So this was the first quarter that we looked into a little bit into detail. Now we go to the second quarter, and there we have two possibilities. The first possibility is to integrate a programming running directly on the Linux platform of the iCube. This means that our iCube is not just a motion controller, but it's a complete computer running on Linux. What does it mean? This means that all files are accessible like in Windows Explorer, which means that we have a consistent file management and file sharing, and also a remote access is possible. All Linux commands are supported, which means that the training effort is reduced. Desktop Linux applications such as Git, rsync, Python, etc. can be used, which gives us the following advantages. Application opportunities which normally are reserved for IPCs can be used here. We have a socket communication, which is possible, and users can configure their own way to access databases like Access or SQL. And we have user permission can be customized, which means that standard Linux commands are supported, and we have a secure remote access via SSH. The second possibility to run a program in the second quarter is the usage of containers. These containers can be compared to a virtual machine on a PC. They have the same existence. Security and portability. Security because the application runs in an isolated environment, separated from the machine code, and portability or transferability is, for example, in case of maintenance, you can easily transfer your program then to the next one. In the third and last quarter, the program is running on an external PC. But also here, the program will run asynchronously to the real-time program on the iCube. The communication between the iCube and the PC goes through RSC, these remote service calls. But what exactly is a remote service call? It's an end-to-end TSL encrypted communication, which is a non-cyclic communication. But the standard security is activated and enables communication between the containers, the PC, or the cloud. This RSC also offers functions such as controlling and monitoring of the device status. It allows you direct access to the global data space. You can send and receive files to the controller. You can create data logging, which can run in a synchronous task. For languages like Java, Python, and C++, we have already libraries available. What are the advantages of RSC? First of all, it's a good alternative to OpenCOA and Modbus TCP, where real-time data exchange is not required. It can be further extended with gRPC. It's a programming language independent protocol developed by Google. It simplifies access and analysis of complex user-defined data structures and arrays. File transfer is possible, and it's a non-cyclic communication, which is ideal for dashboards and data visualization. So first of all, I will show you how to install the RSC library on our iCube. So we open the terminal window for Python in Microsoft Visual Studio. We open a new file and save this as RSC example. In the CLI, the command line interface, we use the pip install command to install the Python PLC Next RSC library. After running this code, the library is getting installed, and at the end, we get the message that this is successfully installed. So now we installed already the PLC Next RSC library. Next is how to set up a connection now. So after the installation, from the library that we just installed, we import the function device into our program. This function needs some parameters values that you need to fill out. The most important one here is the IP address of the iCube. Then you just need to run these few lines of code. And if your laptop is physically connected to the iCube, you can start your communication. You just need to enter the username and the admin and the password of your iCube, which is written on the iCube, and then you are already online on our iCube. So now we are online, and the next step, what we can do, we will read some info and some status data on the iCube. So how do you do that? You also need to import functions from that same library. In this example, we read the article number, or we will read the firmware status, the MAC address, and the status of the iCube. And in the end, we will print this value to the terminal output. So as soon as we now start to start this command, you will see all data that we read from the iCube, like CPU load is here 2%. We see also the temperature is 46 degrees. So these are values that are coming out of the iCube. Okay, another new feature which comes with the iCube is the integrated safety master. We only have two hardware variants in our iCube 9200 series. An iCube without safety PLC and an iCube with safety PLC. The version with the integrated safety master has only an extra board with an extra processor. This option card can only be mounted by a Scala, not by yourself. This FSOE master is a SIL 3 certified safety master, which is fully integrated in the runtime system of the iCube engine. It's a safety profile for transmitting safety critical data over Ethernet. This means that safe and non-safe programming are integrated in one environment. To make the life of a programmer easier, we have a TÜV certified library with the most common FBs that you will need for setting up a safety program, such as emergency stop, two-hand security. You all can find it in our safety library. The safety program can only be written in function block diagram or in ladder. And to check if a program is changed or not, we have a network granular CRC checksum. Here you can see an example with the SLS function, the safety limited speed. If someone is coming too close to the machine and crossing the approximate switch, the machine should change to a safety limited speed. The signal coming from the approximate switch is a dual channel connected to our safety input terminal. These safety input signals are connected to the inputs of the SFGuard FB, and the output of this FB is putting a signal on the safety bus. The signal is read by the server pack, and depending on the parameters in the server pack, the motor needs to slow down to his safety limited speed. So that's an easy example of safety limited speed. Another safety example is shown here as an emergency stop is dual channel connected to one of our safety models, and the inputs are serial wise connected to the safety FB, the SF emergency stop. If someone pushes the emergency button, the output of this function block will generate a signal on the safety bus, and depending on the parameters in the iCube, the motor will stop. We have 15 different safety functions available on our safety card, and we can operate 10 safety functions in parallel on one server pack. These functions are only for monitoring in case of an emergency situation. The way the speed is changing is calculated in the motion controller, but it needs to correspond with the settings on the safety card. If not, we will go to the next safety function, and mostly this is an STO. So if your speed is changing not in the way that it was parameterized on the safety card, we will go into STO. This is a typical old architecture our customers were using in the past. An MP3000 for the motion part, on top of that a PLC for general control of the machine, and a safety PLC for the safety part of the machine, mostly even hardwired. With iCube, the architecture will look like this. PLC, motion and safety are all centralized into the iCube, which means that you only need to manage one program file. And the safety commands are sent over FSOE to our server packs, so not longer hardwired. Also, controlling robots with our iCube has never been so easy, but we need to differentiate here between self-hosted and remote hosted. Self-hosted kinematics are controlled by our server packs like a Sigma 7 or Sigma 10 without any extra hardware. So all kinematics are calculated in the iCube, and we send every cycle new positions to our server packs. In this way, we guarantee a tight synchronization between all robots and also with other auxiliary axes. If you have a frequency inverter or some other server packs, it's really tight synchronized. Self-hosted kinematics are Delta robots, Cara robots, custom-made mechanics. The only disadvantage we have here is the missing of FSU, the functional safety unit. But mostly these mechanics are used in line, and as soon as someone opens a door, the whole line will stop. So it's an easy safe torque off. The remote hosted kinematics, they still need a robot controller, which means that the calculation of the motion path is still done on the robot controller. The advantage with this solution is that you still can use the FSU, but disadvantages are the need of the robot controller and the activation of the MotoLogic feature. But the biggest advantage of controlling robots via the iCube is the common program. So the motion part of the program is written with PLC open function blocks, and these blocks are identical for both solutions. So if you have originally a mechanical solution with a gantry, but suddenly a customer wants to have a SCADA, or maybe later another customer wants to have a GP7, you never need to change your source code. You just need to switch the hardware and that's it. Which robots can we control now? So every robot connected to a DX200, every robot connected to a YOC1000, and every robot connected to a YOC1000 Micro, we can control over MotoLogics. The robot sequence is very easy to program. In this example, we just need to pick a product in point 1, make a vertical movement to point 2, go horizontal to point 3, and place the product in point 4. We return in the same way over the points 5 and 6. As you can see, for every movement, only one coordinate is changing. For example, for the movement from point 1 to 2, only coordinate Z changed from 15 to 400. So we lift. All these coordinates for all movements are written in a structure you see here at the left, which is then connected to the function blocks that you need, and that's all. If we have a closer look to those function blocks, I have here now used the MC move linear absolute. This function block is used if you move between 2 points in a linear way. This corresponds with the move L that you know from robotics. There you need to enter some parameters exactly like you do when you program with the teach pendant. You need to specify, for example, the coordinate system. Is it in the machine coordinates? Is it Cartesian, or are you working in world coordinates? You need also to enter the blend factor you want to use, and so on. So for a normal PLC programmer, it's very easy to program a robot movement. Here you can see a typical architecture of an iCube in communication over EtherCAT with several robot controllers. First of all, on every robot controller, MotoLogix needs to be activated. On the EtherCAT, you can also have some other slaves like frequency inverters, servo packs, or encoders. To be on the safe side, we always say that not more than 4 robots should be connected to one iCube. So the other way was the self-hosted way, and now we should explain which kinematics we can use there. So first, there's the group of delta and SCARA kinematics and all their derivatives. Then we have all kinds of custom-made kinematics which we can control. But here it's better to work together with Yaskawa to get your special kinematic integrated into our iCube. And finally, we have the industrial standard kinematics like T-bots and H-bots. The only limit that we have here are the 64 axes that we can have maximum controlled with one iCube. So if you have, for example, a delta robot with 4 axes, we can control up to 18 of such robots with one iCube. But to make life of a programmer easier, we've developed some generic solutions. The first generic solution that we've developed is the MotoPic for iCube. And as you can see here, the maximum amount of robots that we can control is 16. With this MotoPic solution, you don't need to program your pick and place application anymore. You just need to parameterize. And features like conveyor tracking, vision, load distribution, multi-gripping, pick and place, and a lot more, they are all integrated. But if you want to learn more about these generic solutions, you should join one of the next webinars in this Automation Expert series. Finally, you can see a typical architecture with the safety iCube master. On the FSUE, we can have up to 64 axes, which can be packed into groups like a SCARA group or a Delta group or a Gantry group. So this is already the end of this webinar. I hope it was worth following. And if you have any questions about any kind of motion, we still have 10 minutes left for some Q&A. If you don't have question now, but later, you can always contact us on the email address motion@yaskawa.eu. So Sven, I don't know, are there some open questions?
No, there were a few in the meantime, but I hope all have been answered to your satisfaction, but no, there's currently no further questions.
Okay. Okay, if there are no further questions, we will stop recording. And I say thank you very much